Okay. All right, welcome back, everyone. Today we're going to move through more about probability and statistics. In particular, we're going to finish up the basic rules of probability, talk about some common distributions, then talk about one statistical method called maximum likelihood estimation, and then finally finish up with naive Bayes. We're not going to get to this today. I'll be very happy if we get through naive Bayes. In fact, we have to, so I'll rush to get through that. Because it's on your homework, so you're going to have to use some of that for your homework. So before I start, though, as always, a few quick announcements. On yesterday, we released a midway survey to the course, and we're about at 50% response right now. So if you haven't responded, please do respond. And I'm going to cover this much more on Monday, what the results are. There's a very wide spread, for example, of how much time people spend on the homework, which is not unexpected, but I just want to give people some feedback on what people are actually spending on the course to sort of know how to situate yourself. But there was some very good comments too, which we're going to try to address as much as we can. But one in particular, I think, was actually very valid, and this hopefully also addresses some of the extra time that people are a little worried about now that we're going to have the tutorial and the project due concurrently with homeworks. At least that's still the current schedule. And this is that a lot of the homeworks, it seems like, there's interesting elements to it, were all the comments, but a lot of time is spent kind of digging through documentation on calls that we don't cover in class, right? So a lot of it's been dealing with pandas, right? And sort of figuring out what all the calls do and looking at calls that really you didn't know how to find in the first place. So some of that is data science, right? Some of that is just what you're going to have to get used to in order to be a data scientist, if that's the path you want to pursue. But I think we can probably do a little bit better than this, what we're doing right now when it comes to this. It's just a reality. So we're going to try to do this for the remaining homeworks. So for the remaining homeworks, and that means probably on Friday, but stay tuned for that more details there. I realize that's kind of going to be playing a little tight for homework 4, but that's sort of sadly the reality of the situation. We're going to try to have a recitation section for each of the homeworks that's going to cover the functions you need to use for the homework. Of course, not how to use them in the context of the homework. It'll be just on dummy data, but it'll at least cover all the functions, the inputs and the outputs of those functions, and let you know how to use those things. So hopefully that will address some of the problems people are having with just not knowing knowing how to do something conceptually, but not knowing how to actually implement it in practice. This will at least give you a baseline for how to do that. So I think this was one very sort of valid point people were raising, and as we said, this is a first-time course, so we're going to try to adjust a little bit, course correct a little bit midstream here, and start doing this for the rest of the homeworks. And hopefully, this will decrease the amount of time people spend on the homeworks, and you'll make it a little bit more balanced in terms of the other topics. So that's likely going to be this Friday. We have to just put it together, so it's going to be kind of rushed, this one. The next ones we'll do more at the start of the homework, but that's just the one comment I'll make so far because it's sort of pressing for the next homework. I don't want to wait till Monday to talk about that. The rest of the things, though, in terms of the sort of average response rates and everything, or sorry, in terms of the average responses, we'll discuss a little bit more on Monday. Any questions there? Okay. Sound a good idea for everyone? Everyone seems to think that's a good idea. At least you don't have to go, so it's not going to be a bad idea, hopefully, but hopefully it'll be helpful. All right. So where we ended up last time was talking about some basic rules of probability, and we finished up talking about marginalization. The next thing I want to talk about is something that probably most people here have seen at least a little bit before, but it's Bayes' rule. So Bayes' rule is actually just follows directly from the definition of conditional probability and, well, it's just directly from the definition of conditional probability. So the idea here is that if we have some variables, random variables x1 and x2, by definition, this is equal to the joint probability of x1 and x2 over the probability of x2, right? Which is also equal to, we can write this one kind of either way. We can either have it x1 given x2 or x2 given x1, which is also equal to the probability of x2 given x1, probability of x1 divided by probability of x2. And I'm writing out one more thing there, which is just sort of also, you can write this term here by summing out, by marginalizing out over x1. Right? So then it looks like you have terms that look just like the numerator, just you're summing out over x2 in the denominator. Sorry, over x1 in the denominator. So this is actually just, I mean, it seems, it's called a rule, but really it's just basic manipulation of probabilities, right? The actual equations are. But it leads to some interesting things. And I think this is why it's gotten so famous, is it leads to some seemingly counterintuitive results that are, of course, based completely in fact. So have people seen examples like this before, by the way? Who's seen this example before, or something just like it? Okay, most people. So the idea here, well, maybe not most people, but some people. So the idea here is, let's say we have a question like this. So I want to know if I have some rare strain of the flu. This flu is very rare. It occurs in only 1 out of 10,000 people. And there's an accurate test. I'm putting accurate in quotes for reasons that will be obvious shortly. That tells me if I have the flu, it tells me that I have it 99% of the time. And if I don't have the flu, it tells me I don't have it 99% of the time. And so I go to the doctor and I test positive for this flu. Now, what's the probability that I have the flu? Right? And we'll write it out in a second, or maybe we'll at least give a quick sketch of the computation in a second. But when people sort of hear this, they naturally think, oh, it's pretty high. If the test is 99% accurate, it should be pretty high. But actually, the probability of the flu here is still less than 1%. Right? And this follows just right out of Bayes' rule. So if we say x1 is the flu, and x2 is the test, well, they aren't equal to those are just what they're describing. What we're trying to actually estimate here is the probability of x1 given x2, right? That's what we're saying, what's the probability that I have the flu? Specifically, what's the probability that I had the flu given that I tested positive? So probability of x1 given that, or rather maybe probability of x1 equals 1 given that x2 equals 1, right? So we're trying to estimate. And so the way you do this is you just write out the terms, you write this out using Bayes' rule. We don't really know this distribution ahead of time, right? We're not given this actual distribution ahead of time. So we're going to write this out using Bayes' rule. So this is going to be the probability of x2 being equal to 1, given that x1 is equal to 1. This is the probability of the test being positive, given that we had the flu. We do have that. That's 99%. Times the probability that x1 equals 1. We also have that. That is the 1 over 10,000 term. Divided by, well, we're going to sort of use the rule from the on the rightmost side there. The probability that x2 equals 1, given that x1 equals 1, probability x1 equals 1, plus, I'm going to run out of space here, but I'll try to condense. Probability that x2 equals 1, given x1 equals 0, and the probability of x1 equal to 0. Okay, sorry for being a little bit off the board there. So we actually know all these quantities. So this one here is 0.99. This one is 0.0001. This one is the same as above there, so 0.99, 0.0001. This one here is the probability that I test positive for the flu given that I don't have it, so that's 0.01. And this one is the probability that I don't have the flu, which is 0.9999. Right? And if you multiply this out, you get something around 0. I think this is right, like 98 or something. It's about equal to that. So the counterintuitive thing here is that the probability of not having the flu is so great that actually this term is substantially bigger than this one, even though the test seems accurate, right? Even if you test positive, you're probably in that 1%, chances are, because not many people have that flu. Right, so that's the idea of Bayes' rule, and I think that's the reason why it gets gets famous for a lot of reasons. But I think part of the reason why it gets so much attention is that it does lead to kind of things that are, of course, factually correct, but they just seem a little counterintuitive. Any questions there? All right. Now let's talk about independence. And actually, independence is going to play a really key role through a lot of the rest of this lecture. So I want to spend not too much time on it, but just give the definitions here. So we say that x1 and x2 are what are called marginally independent if the probability of the joint probability of x1 and x2 is equal to the product of the probabilities of x1 and x2. Now again, remember, what are these things, right? This thing here is a distribution over, for all possible values of x1 and x2, what's the probability? This one's the same thing, right? Because you can just take all possible values of x1 and x2, plug it in there. And this has to be true for all possible combinations of x1 and x2 in order for this to actually be, these two variables to be independent. Another way to write this is that the probability of x1 given x2 is equal to the probability of x1. Right? Because essentially what this is saying is that, and by the way, the reason this is the case, it's written there, but the probability of x1 and x2 is just the probability of x1 and x2 over the probability of x2. That is the definition of conditional probability. Now we're going to use independence here. Probability of x1, probability of x2 over probability of x2. And of course, these two terms cancel, so you're just left with x1. And so just to be clear, these are equivalent statements. But this is a little bit more intuitive maybe sometimes because it says that the probability of x1, our distribution over x1, given x2, is just the same as our distribution over x1. In other words, knowing x2 doesn't give us any information about what x1 might be. Right? We have the same distribution. In other words, it doesn't help us determine what x1 might be. And similarly, actually, it holds the other way too. So probably x2 given x1 is also just equal to x2 for the exact same reasons there. This also leads to our second idea, which is conditional independence. And this one is a little bit trickier to follow, though the definition is easy, but conceptually what it means is a little bit harder. The most important part, I would say, of conditional independence is that is this point here, is that marginal independence, so two variables being independent, does not mean that they are conditionally independent. All right, so the two variables can actually be independent, but if we know some third information, they are no longer independent. All right? So that's actually very possible. And similarly, if they're variables conditionally independent, that does not mean that they are marginally independent. We're not going to go too much into detail about the sort of examples of these things, but just know that that is in fact the case. Okay, so conditional independence is the same thing, but with conditioned on some third variable, x3. So it's saying that probability x1 and x2 given x3. By the way, these are all big x's I'm writing here, but of course they'll hold for any instantiation of little x as well, any value you assign to x. This is equal to, so this is marginal independence here. And this is conditional independence. And this says that this is equal to the product of the two conditional distributions, x1 given x3, and the probability of x2 given x3. And this is also equivalent to saying that the probability of x1 given x2 and x3 is equal to the probability of x1 given x3 only. In other words, if I know x2 and x3, I know no more about x1 than if I just know x3. So I can kind of ignore x2 for the sake of these probabilities. And that follows from the exact same kind of derivation there. I won't write it out again, but it is in the slides. Questions? All right. Expectation. And here I'm actually going to skip some of the later derivations. They're in the slides kind of for reference, but I'll just highlight the results themselves. So an expectation of a random variable is just equal to the of big X. By the way, expectations now, I'm still using them as they are a function of big X, right? They take a random variable as their input because they're a function of the whole random variable, but they themselves are not a distribution, or they themselves are not a dictionary. They are just a number, right? And this number is equal to the sum over all values X can take on of that value times the probability of that value. Okay. And these sort of have very natural interpretations. For example, if we have a binary variable, take some values of 0 or 1, its expectation will just be the probability that's equal to 1, right? Because it'll be 0 times the probability that's equal to 0 plus 1 times the probability that's equal to 1. In other words, just the probability that it's equal to 1. But it's sort of very important to remember that expectations only make sense when the random variable takes on some numeric quantity. So I could not, for example, ask what my expected weather was. If weather was this categorical variable that was either sunny, rainy, snowy, or cloudy, it would not make sense to even talk about the expected value of a variable like that. That just what's halfway? What's the 0.1 times snowy plus 0.2 times cloudy, right? This doesn't make sense. So expectations only make sense when the actual values here are numeric. Otherwise, this expression is sort of meaningless, right? And so that's actually an important thing to keep in mind, too, when you talk about even things like binary random variables. This only really makes sense to talk about their expectation if they are, in fact, actually, the 0 and 1 mean something. If those mean just sort of arbitrary things, then it doesn't really mean anything to talk about their expectation. I guess just sort of keep that in mind, because when you think about expectations, a lot of the same rules as probabilities apply, but they only make sense in a limited subset of cases. Now, there are a few nice rules to know about expectation, which I'm not going to go through here. They're very straightforward, but they are a little bit involved, actually. And so the first one is that maybe I'll have to write the rules here. I won't write their proof. The first one is that if I have two random variables in both these cases, then the expectation of x1 plus x2 is equal to the expectation of x1 plus the expectation of x2. This is called sometimes linearity of expectation. You can also multiply them by a scalar, and the same thing holds. But this always holds regardless of whether x1 and x2 are independent. And the proof is here. You basically just go through the definition of what expectation is, and you use the rule of marginal probabilities, and you get out this fact. The other thing that is interesting, the other sort of relevant fact, is that the product of x1 and x2 equals the product of their expectations if if x1 and x2 are independent. So that only happens in some cases. That will not hold if they are not independent. But if they're independent, then this holds. Few more quantities that are of interest here are the variance of x. The variance of a random variable is equal to the expectation of the random variable minus its expectation squared. So this is equal to the expectation of x minus the expected value of x squared. I'll also, by the way, refer to the expected value sometimes as the mean of x. It is also called the mean. It's the average value that x takes on in that sense up there. And so mean and variance might be more common terms you've heard before. But the variance is just the if I look at x and see how much it differs from its expectation, and then square that value, the expected value of that value is the variance. And so the idea being that if x always takes on its value, its expectation. In other words, say if x only has probability 1 that it's equal to some value, and that takes down that value all the time, that would have 0 variance because it's always equal to that same value. So this term is always 0. Whereas if it takes values that are often very far from its value, it would have high variance. It's also sometimes handy to write this as the expected value, and this is just sort of straightforward manipulation that's on the slides again, of x squared minus expected value of x squared. This also, there's a generalization of this to 2 random variables, which is called the covariance. The covariance of 2 random variables is the expectation of x1 minus the expected value times x2 minus its expected value. So this, unlike, the variance is always positive, right? Because this term inside is always positive. The covariance can be negative, though, because one of the terms could be positive, one could be negative, and that actually could happen. And you can also write it as the expected value of the product minus the product of the expected values. And so these are hopefully things that are you've at least seen before. If you haven't, somebody actually emailed me about this, and I'm trying to find a reference. We'll send it out shortly. I'm trying to find a good reference that I like on this, actually. I've seen a few, and we're trying to find a good one, so we'll try to send it out by today or tomorrow for those that have asked. But this is quite fast. The reality is you're not going to have to use this too much, but this is hopefully actually, even in and of itself, a reasonable reference to go back and cover kind of the entirety of the things you may ever need to use. Well, in this course. What was the question there? So when you have multiple random variables, covariance is usually talked about as a matrix. So you talk about a covariance matrix of all possible pairs of covariance. There's not one that usually is thought about like with 3 terms in that product there. Those actually do exist, but they are much less common than taking all possible pairs of random variables. Just because they get to be a lot of them very quickly, right? If you're talking about all possible sort of triplets now, and there could be a lot. So for multiple random variables, it's more common to talk about the matrix of all possible covariances. Okay, any questions? All right, chugging along. Infinite random variables. So far, and I think in my emphasis of saying, what are these things? These random variables, these things are dictionaries. They map settings of your random variables to actual values. This kind of breaks down now when we talk about infinite valued random variables, of which there are some, both discrete infinite valued ones, so they'll say distribution over all integers, and continuous random variables too. So I'm going to now deviate a little bit from what I said before, because now instead of these distributions as being, so now instead of p of x, when we have something like an infinite distribution, instead of p of x really being a dictionary, we obviously cannot represent a dictionary with an infinite number of keys. So now you should really think of p of x. And again, that's sort of the big of px. You should think of that as a function. Right? So p of big X here is a function. Boy, I've used up a lot of chalk this lecture so far. So p of big X you should think of as a function. Right? So just like before, we had, this is the big X, trust me. Just like before, we had P of big X, meaning the entire set of all probabilities. Here, P of big X will kind of refer to the entire function. So, for whatever value of X, I have to specify how I'm going to compute that probability. And now the kind of confusing thing is this is usually written in terms of what this equals. In other words, it's usually written as P of little x equals some function of x, right? But it's important that, when I'm writing P of little x here, I'm going to sort of specify what that function is. And I'm talking about, though, a specific value, a number that you get as the output of that function, whereas this one's going to talk about the entirety of the function. It might be a little bit more common here to just call this first one P, and this next one P of x. That might be a little more common, but I'm kind of going to try to keep with my convention, and that is the generalization of my convention to other, to higher dimensional, or sorry, not the higher dimensional, to infinite random variables. Okay, so the nice thing about this is actually everything pretty much stays the same. So we can have distributions, certainly, over infinite numbers of values. An easy one would be something like the probability that x is equal to k, for k being an integer, would just be equal to, or a non-negative integer, positive integer, so 1 to infinity, would be equal to, say, 1/2 to the k, right? This is called a geometric distribution, which we'll talk about in a second, but this is a sort of a simple example of that. And the idea here is that this term here sums to 1, right? Because the sum overall I, or really, I mean, I won't even write it out, but hopefully everyone has seen this before, that 1/2 plus 1/4 plus 1/8, etc., that's equal to 1. Right? So we still have the number of values is infinite. K here, the value that the variable can take on, is infinite. It ranges from 1 to infinity. But the probability decreases in such a way that the sum over all possible values is still equal to 1. Any questions there? Okay, and next, this will also generalize, well, with a little bit different notation now, to continuous random variables. So that was the case of discrete but infinite random variables. And you can also talk about continuous and, of course, therefore also infinite. For those that are sort of math people, I'm talking here about countably infinite variables, whereas here I'm talking about uncountably infinite variables. But don't worry if you're not. Those terms are unfamiliar. The idea here is that we can do the same thing where we now specify x as a function, but instead of having the rules be about sums, because you can't take a sum over a uncountably infinite thing, we're now start talking about integrals. So we just as before can have the same notation for specifying distributions over continuous random variables. The difference is that these are p of x is now called a probability density function. Instead of a probability function, also called a PDF, because it isn't actually a probability anymore. There's obviously an infinite number of these, so you can't sum them all up and get 1. The analog, though, is that the integral over all x, but integrating over the whole real line of p of x dx equals 1. There is very little integral calculus in this course, actually, so I'm not going to make people actually compute any of these integrals. There is derivative calculus. You have to know derivatives, because that's actually very useful for optimization. Integrals are not as common, at least in most machine learning and data science. But just definitionally, this sort of is what you have for a probability density function instead of a probability function. And the other thing that might be useful to just know about is, and I should say that all sort of the other rules kind of generalize similarly. So, for example, the expectation of a random variable x, if it's continuous, it would be equal to the integral of x times the density of x dx, right? So you take the value multiplied by the density function and integrate that over the whole real line. The other thing that might be useful to know is something called the cumulative distribution function. Or CDF. Important that this is called the probability density function. This is the cumulative distribution function. So the d there is different. There's no such thing as a cumulative density function or a probability distribution function. This is equal to, this is now, the problem here is that we don't actually have probabilities here, right? This is some density that isn't quite clear what it actually means. So the way to get probabilities out of this is to integrate this function. And so the cumulative density function, which we write f of a, is equal to the probability that x is less than or equal to a, which is equal to the integral from negative infinity to a of p of x. So that's actually, oops, I forgot the dx here. But those are sort of the basic properties of continuous distributions, and we're going to see a lot of these we're going to see a couple of these at least in a second. By far the most common one that you'll see, well, I'll leave that to later, but they're coming right up, so you don't have to wait too long. Okay, so any questions now? So actually that is it for the basic rules of probability that we're going to use as this class is concerned. Of course, there's much more you can talk about in probability. If you really want to ground yourself kind of in true probability, you actually needed some pretty advanced math to sort of know what these kind of integrals actually mean, and what we really mean by these, and what functions you can integrate and you can't integrate. But we're going to ignore all of that and just kind of use it at a mathematical but fairly informal level too. So let's now talk about, and this will be actually quite fast because this is more just definitional. I want to talk now about some common distributions. And actually, we've already seen these before. At least, some of them we've already seen in examples before. I just haven't given them these names. And so this will just actually clarify a couple things. It'll clarify the names of some of these things, as well as how we often sort of define them in terms of what are called their parameters. So let's talk about the first thing of being a Bernoulli distribution. So this is a distribution over 0, 1 random variables. And that is exactly what you sort of would expect. You have a variable x that can take on values in either 0 or 1. And it takes on value 0 with probability phi. So probability over x, and the probability that x equals 1 is equal to phi. Some number phi between 0 and 1. Now, the only reason I'm actually being pedantic here about this is that I'm going to write this in a certain way. And this thing you're going to have to kind of get familiar with because I'm going to use this notation a lot. And this thing phi here, phi or phi, depending on how you want to pronounce it. I might switch back and forth. Apologies for that. Phi here is what's called a parameter. So this is a parameter of the distribution. In other words, this parameter characterizes what this distribution actually is, right? You only need to specify one of these two, of course. You only specify the probability is equal to 0, because we know the probability is equal to 0 is going to be 1 minus phi. Right? So we only need one parameter to specify this distribution. Namely, and by convention, we use the probability that the random variable is equal to 1. And the way I write this is I write this as the probability. So I'm actually going to change the notation a little bit. I'm going to write this as the probability of x semicolon phi. And the way I say that is the probability of x parameterized by phi. Okay? And all that means is that phi is the parameter governing that distribution. In the case of a Bernoulli variable, that parameter would be one value. That would just be what's the probability of it being positive. So it's kind of almost too obvious. You don't even think of it as really being a parameter. But for a lot of more complex distributions, you really need to think about these as parameters because they don't have any nice interpretation other than that. A couple other properties there is expectation is equal to also phi, but again, only do that if you have if the 0 and 1 actually are meaningful. So the other thing we've already seen before, in fact, is a categorical distribution. Sometimes called multinomial, but often multinomial actually refers to a distribution where you have multiple draws from a categorical variable. So I'm going to try to call it categorical, though sometimes I slip and call it multinomial myself. But it really is supposed to be categorical. I think I actually might have slipped up on the homework and called it multinomial. But this is the one we're talking about. We're not going to care about like binomial or multinomial distributions in their kind of true sense. So this is a distribution now over multiple values. So this is actually probably what we saw before, right? X can take on any number of values, say 1 to k, right? And this distribution is parameterized by k minus 1 numbers. Phi 1, so this is Bernoulli. This is now categorical. This is categorical. Now you have k minus 1 parameters, phi 1, phi k minus 1, where the probability that x is equal to I is just equal to phi I. So these things here, I first wrote it as 1 to k. Okay, I'll write it first as 1 to k. So these numbers just specify the probability that variable takes on one of those values. So phi of I just encodes the probability that x equals I is just equal to phi of I, right? And the constraint, of course, being that these numbers have to sum to 1. Because of that, you could actually also just use 1 to k minus 1 of them, because you know the last one has to be equal to 1 minus the sum of the rest, right? So you could actually use k parameters or k minus 1 parameters depending on how much you want to constrain your probability, your parameters versus how much you want to have like one parameter that's dependent on the rest of them effectively. Now here again, it doesn't really make sense to take expectations unless those i's really are meaningful. So if there's like ratings or something like that, then that might be meaningful to take an average. But even there, it's not always relevant. And this actually ties in a lot to our discussion way back about the types of ways you evaluate or visualize different types of data. So in other words, if your data is categorical in nature, probably doesn't make sense to talk about or even ordinal, it doesn't make sense to talk about expectations, versus when it's numerical, you actually can talk about expectations. OK, so let's move on to a few others. These I'm just going to I'm not going to write anything on the board about them, but they're good to know about these. One of the more common infinite discrete valued random distributions is the geometric distribution. This is equal to, the probability that x equals I is equal to 1 minus phi to the I minus 1 times phi. And what this is this is the probability that if you have a Bernoulli random variable, what's the probability that it takes you I times before you get a 1? Right? So to get a 1 on the ith time requires that I get 0 the first I minus 1 times. So that's 1 minus phi to the I minus 1. Then times phi to the I. So then I get an ith on my last one. And it's pretty easy to check that this also does in fact sum to 1. And now I'm going to start plotting these things a little bit. So this is the plot of the distribution. What it shows on the y-axis there, this is for phi equal to 0.2. What it shows on the y-axis there is the probability that x equals I, and then the probability. And on the x-axis there is I, the value it takes on. Another common one you may see for discrete variables is the Poisson distribution. We're not going to use it that much, but it's so common that you probably should at least have heard about that. It's really good for analyzing the number of events that occur in a certain interval. So if I want to know, how many buses are going to arrive in, I have buses on my mind because we're talking about the homework recently. But if you want to know how many buses are going to arrive in an hour, say, or actually in any interval, assuming they have some distribution, and also often in practice, the Poisson distribution is a very good model for that. So it's distribution over discrete infinite variables, so it's distribution over counts, right? This actually should be 0, I believe, here. So apologies for that, because it goes from 0, not from 1. I think I cut off this figure. So if I want to know, how many buses are going to come within an hour, if I plot that, chances are you'll have some distribution that looks like this. It can't ever be less than 0, right? Because you can't have negative buses come. You'll probably have some increases, and the chance of a whole lot coming are less and less. Though waiting for the bus, it seems like oftentimes 5 buses will all come in a row for some reason in Pittsburgh. I don't know why. It's governed by this parameter called lambda. And lambda here, again, now we're moving to a point where it actually lambda happens to be its mean. But really, lambda is just a parameter that governs what that equation actually says, right? It's not clear from that equation that lambda is the mean of this distribution. It turns out that it is, but it's actually not that easy to show that. It involves showing that this infinite sum of x or I times that thing is equal to lambda, which is doable, but not that easy. Not that obvious like the geometric one. Even the geometric one actually takes a little bit of work, but this takes more work. So now you're really thinking about this is just a parameter of the distribution, right? It's just the number that characterizes that distribution. And by varying lambda, what you actually get is you get a distribution that's shifted more towards the left here or more towards the right. So this mean here, the little hump here, shifts out more this way or more that way. That's just sort of empirically what changing lambda there does in the Poisson distribution. OK, so now let's move to the most common distribution you're going to see for continuous random variables, which is the Gaussian distribution. And when I say most common, I want to be very careful here. I mean most common in people doing data science, not in the actual data itself. So oftentimes variables are not Gaussian, but people will still use Gaussian assumptions on them to, better or for better or worse. But in terms of the actual things you will see, in terms of the algorithms you will see, it is by far the most common distribution to use when you have real valued data. And there are some good reasons for this. For example, there's this nice property called the central limit theorem that says that under certain conditions, if you have a sum of random variables and look at their mean, that mean will actually be distributed according to a Gaussian distribution. And that actually holds, again, in some cases, it holds true regardless of the distribution of the individual variables. Their mean will be a Gaussian. So it's actually kind of surprising, but is a property that holds. So the other reason why it's so commonly used is that it really is just very, very easy to manipulate. Despite the hairy-sounding, hairy-looking form of this equation, it's actually one of the nicer equations to do things like integrate. There aren't many functions you can integrate nicely over multidimensional spaces, but a Gaussian is one of those. And so you can do that here. And so that's something you probably has something to do with why people use it so much, is that the math works out nicely when you use it. Anyway, now this plot here shows, I'm sure probably everyone's familiar at least or seen a Gaussian before. But what this plot shows the Gaussian density, P of x. Again, it's not a probability, it's a density function. But it shows the density versus x for the Gaussian with mu 0 and sigma 1. Mu here is called the mean of the distribution, and sigma is called the variance of the distribution. It just so happens that these are the two parameters that govern a Gaussian distribution. Now, it just so happens that these two parameters are also equal to the mean of the distribution, the expectation, and the variance of the distribution. But there's no reason actually to know why that would be the case ahead of time, right? There's no reason to. It's not at all obvious, completely unobvious. Maybe the mean, because it's symmetric, is somewhat obvious, but actually even that is not obvious because you can still have distributions that actually have no mean that are symmetric. So they can be really weird things can happen when you talk about integrals again. But the fact that the variance of that is equal to sigma, or that the mean is equal to mu, is actually really not at all obvious to me. You have to actually compute the integral, right? The expectation is equal to the integral from negative infinity to positive infinity of x times p of x. So why on earth is that equal to mu? It is. And the best way I know how to do this involves complex valued transformations of integrals. So we will not do any of that. Just know that if you do compute that, it is equal to mu. And if you compute the variance, which is the expectation of x minus mu squared, that will equal sigma squared. I'm not writing that very well, but if I take the expectation of this minus mu, that will equal squared, that will equal sigma squared. And that's actually why you can actually parameterize them in other ways too. But the reason why people use sigma squared and mu to parameterize it is that those are sort of naturally interpretable functions. Notice I'm also using sigma squared here, not just sigma, because sigma squared is the variance, and generalizations to say multi-dimensions always use the variance, not the standard deviation, which is the square root of the variance. So I will always use sigma squared as the parameter, not sigma. OK. The one thing I'll say is that, and we'll talk about this a little bit more when we talk about anomaly detection, because that's where we're going to use multivariate Gaussians. But the multivariate Gaussian is one of the few distributions that actually generalizes well to higher dimensions. So for the vast majority of cases, if you take a single variable distribution and think about what its extension is to higher dimensions, it's really hard to do anything with that unless you just think about a product of independent distributions, which is not very interesting. So if you think about really what really should be the generalization, most distributions are kind of nasty. The Gaussian is an exception, and the Gaussian has this very nice form here. This term inside here is a determinant. This matrix sigma is called the covariance matrix. It actually is the matrix of all possible covariances, the different elements, and mu here is a multidimensional mean. So don't worry about this. Just know that we're going to see these more later, and Gaussians are nice because they are one of the few distributions we actually can estimate nicely in high dimensions. Yeah. Mu, yeah, not u here. And do that very fast. Mu. I'm fixing these right when I do that because otherwise I just forget after class. Okay. A few more we're going to just throw out there. The Laplace distribution essentially is like a Gaussian, but you replace the squared term with an absolute value term. And so whereas the Gaussian looked like it had this what's called a bell curve shape, right? So it looks like this sort of smooth thing on top. The Laplacian has Laplace distribution, sorry, has a sharp peak. And the other factor of the Laplace distribution is that it has what are called heavier tails. So the Gaussian tails, because you have in the distribution here, you have a x minus mu squared. This term, for x getting far away from u, goes to 0 very, very fast, right? Because this thing gets big, and so negative of a big thing goes to 0. So these things go to 0 really quickly. They tail off very, very quickly. The Laplace distribution, because it's only absolute value, now does not tail off so quickly. And actually, there's a very close connection here between these methods, which we'll talk about next time, not this time, and do it briefly. There's a very close connection between these methods and the squared 2-norm loss versus the absolute, or the squared loss versus the absolute loss. So this one has an absolute function here, and so basically you don't quite tail off quite as fast. So it goes to 0, still exponentially fast, which is pretty fast, right? But a little less fast than that. Less fast than the Gaussian. And then finally, there's also the exponential distribution, which is like a one-sided Laplacian. It's Laplacian. Oh, sorry, I keep calling it Laplacian. Just Laplace distribution. Laplacian is something else. The exponential distribution is like a one-sided Laplace distribution, and it's often used to model things like arrival times. So if I want to know how much time it's going to be before the next bus comes, actually, it's frankly, empirically, it's very often fit well by an exponential distribution. Again, whether that's true in Pittsburgh or not, I don't really know. Okay, and then finally, some things that we're going to not talk about right now, but which may come up later in class, are because they have to do with hypothesis testing in particular, are the student's t-distribution. Student is the author that published the paper, or he published it under the name student, and so that's why it's called the student's t-distribution. There's also the chi-square distribution, which is a distribution of a Gaussian variable squared. And things like the Cauchy distribution, those are not very common, but Cauchy is kind of interesting because it actually has no, even though it's symmetric and it integrates to 1, it has no finite expectation. Actually, not finite or infinite, actually. It has no expectation. It's undefined, which is kind of very weird. So when you have continuous random variables, the upshot of this is things can happen that are very strange. You can have things that, variables that have no actual expectation, even though they are centered right on 0, and fun things happen. Okay, so now I'm gonna move on with the rest of the class now. I do want to move on because I want to cover both this and the next section. I want to now move from probability to statistics. So as I said at the beginning, probability really is about mathematically describing distributions, whereas statistics is about taking data and finding distributions that fit well to that data. Right? Now, of course, the question is, what do I mean by some distribution describing the data well? It's very kind of arbitrary, and it's very hard to do in general. So if I have some data, how do I find a distribution that captures that data? Well, if it's completely arbitrary, the choice of distribution is actually quite difficult to do. If my data is, say, real valued, right? It actually can be very hard to do. But the question becomes much easier if I talk about it in a more restricted sense and say, if I have some parameterized family of distributions, say the Gaussian distribution or the Bernoulli distribution, how do I pick the parameters that that make that distribution fit the data the best. So this comes to the question, or this leads us to at least to one method for doing that, called maximum likelihood estimation. And I want to emphasize that despite this seeming obvious, it is not the only way you can estimate parameters. There are other ways that are actually arguably just as good. But it's very common, and I think that at least in machine learning, this is by far the most common way you estimate distributions. So the idea is actually very simple. Suppose I have some data, x1 to xm. And I want to find a distribution that fits this data. Or rather, I want to find parameters. I have m examples always here. And I want to find some distribution, parameters, that fit that data well. Well, I can characterize what the probability of this whole sequence is under that distribution. And this, again, this actually is something called the independent identically distributed assumption. So we're assuming that each of these data points has the same distribution, so the same value of theta, and we're going to assume they're independent. So the product of this joint set here is just equal to this product from I equals 1 to m of the probability of xi and theta. Right, that's the probability of the data under the distribution specified by that parameter. And all maximum likelihood says is, I'm going to pick, as kind of the obvious thing, I'm going to pick the theta that maximizes that probability. This is sometimes hard to work with. This term here, it's a product of terms, can be kind of hard to work with. So oftentimes we actually say this is equivalent to maximizing over theta of the log of this thing, which would be the sum of the log probabilities of xi given theta. And we even have a term for this whole thing here. This is called, the sum from I equals 1 to m. This is called the log likelihood of the parameters. Sorry, it should be log likelihood of the parameters here. Actually, both of these are sometimes in different contexts, but log likelihood is usually talked about parameters. OK, so let's go through one example of this now, because this seems obvious, but it also seems like there's a lot of, kind of a lot of abstract things here. So let's talk about a Bernoulli random variable. So Bernoulli, again, we talked about before, it just means that the probability of a distribution over binary random variables where the probability of the variable being 1 is just the parameter phi. So now, suppose that we want to, we have some observed data. So each of these data points will either be x superscript I will be either 0 or 1. Actually, I actually didn't want to leave that hat on phi there, so I apologize for that. There should be no hat there. I didn't want to bother with hats and things like this. I'm just going to use the same thing, and you have to figure out whether it's an estimate or something else. So given some observed data, what should my value of phi be? Well, this one seems kind of obvious, right? Of course, all we do is we take, the number of ones I got. What's the probability of xi equals 1? Well, it's just the number of ones you see in your data. Phi should just be equal to the number of ones, which is just equal to the sum I equal 1 to m of xi, right? Because it's 1 if it's 1, otherwise 0, divided by m. Where m is our total number of examples, right? That's obvious. What else could it possibly be? Well, actually, it could be a lot of other things too. That one does seem pretty obvious. But if I only have, say, one observed data point, that's probably not the best estimate, actually, because it'll either estimate 0 or 1. Maybe I want to add some smoothing or something like this that says, OK, I'm going to add 1 to the numerator and divide by 2 plus the denominator. So why is this actually still a reasonable estimate? Why do we want to do that? Well, this one actually, in the case of Bernoulli, there aren't many other estimators you can have except This one if you want to get really fancy, but then you have to specify some other things as well. So most estimators will give you the same answer for the Bernoulli variable. But let's see why this is true from maximum likelihood. So the likelihood for a Bernoulli variable is the product from I equals 1 to m of the probability of xi given, in this case, phi. I'm going to use theta to describe parameters generally, but in the case of a specific distribution, I'll talk about those parameters. So for Bernoulli, it's going to be phi. The probability here, I'm going to write this in a kind of a handy way for doing these manipulations. I'm going to write this as the product from I equals 1 to m of phi to the xi. Right? So that is phi to, if xi is 1, that'll just be phi. If xi is 0, that'll be 1. So it won't affect the product. Times 1 minus phi to the 1 minus x I. So again, if this is 1, I get phi. If this is 0, this will be 1. Right? Because, sorry, if this term is 1, this term is 0, so this whole term is 1. This is phi. And otherwise, this is equal to 1 minus phi. So in other words, this whole thing here is equal to phi if xi equals 1, and 1 minus phi if xi equals 0. Just sort of a handy way of writing that. Which is exactly what we want, right? We want to say that the probability of it being negative 1 is 1 minus phi. Sorry, 0 is 1 minus phi, and the probability of 1 is phi. OK, so now I want to write my, I now want to find the parameters that maximize this probability here. And it's actually kind of tricky to work on these things. So I'm going to take the log of it. It's a little easier in the log domain. I'm going to take, now I want to maximize over phi of the sum from I equals 1 to m of the log of that, which is going to be xi log phi plus 1 minus xi log of 1 minus phi. And I want to maximize this whole thing over phi. OK, how do I maximize that? Well, we know already that the way you maximize or really optimize any function is you take the derivative instead of equal to 0. I could be thinking about minimizing the negative of this function or maximizing it. Both ways, you set the derivative equal to 0. So the derivative here, let's take derivatives then. So the derivative here is equal to put the phi of the log likelihood of phi is equal to the derivative of this thing. With that, that's just going to be, well, first of all, it's the sum from I equals 1 to m of xi over phi minus 1 minus xi over 1 minus phi. Right? I'm just using the fact that the log of the derivative of the log of x is 1 over x. Okay. All right. This whole thing. And to optimize it, I just want to set this equal to 0. Sounds like a lot of work just to get the fact that we're going to divide by the total number, but this is very general and it'll apply to a lot of other distributions as well. Okay, so moving on. That's our basic strategy there. How do we do that? Oops. I can kind of see that still. Okay, how do we do that? Well, if we just write this out a little bit more, that term there. This term, being equal to 0 rather, means that I'm just going to distribute the sum into those guys. So what this means is that the sum from I equals 1 to m of xi over phi is equal to the sum from I equals 1 to m of 1 minus xi over 1 minus phi. Okay? So again, this term here, the sum over all xi, and I actually can move the sum into the numerator here. That'll be just the count of the number of times xi equals 1. This one will be the count of the number of times xi is equal to 0. Okay? So I'm actually just going to call this, for the time being, let's call this term here, this whole sum here, a. So this is saying that a over phi equals over 1 minus phi. Minus phi. In other words, a times 1 minus phi equals b times phi, or phi equals a over a plus b. In other words, phi equals the sum over the number of times we've seen a 1 divided by the number of times we've seen 1 plus the number of times we've seen a 0, which is the total number of examples we've seen. So that was a lot of work to get this fact that to estimate a probability, you count the number of times you've seen something and divide by the total number of things you've seen. But really, this is an incredibly general principle. And there are other situations, some of which we'll see next time, where this is actually, it's not at all obvious what the right answer is. And so in fact, you can derive a lot of machine learning algorithms, their loss functions, through the principle of maximum likelihood. And there it's not at all obvious that these things, you should be minimizing, say, a squared loss or logistic loss, right? That's not at all obvious, but they fall out of very nice sort of characterizations of the distributions and then maximizing likelihood. So that's why I kind of want to go through this a little bit and emphasize that this is not there's a reason why you actually, or there are actually many reasons, but there's a reason why you actually would estimate the probability by essentially counting and taking proportions. Yeah, there's a question?
Are we trying to figure out what the distribution over here or the estimate of the parameters?
We are only trying to figure out the estimate of the parameters. We're saying I assume the distribution is a Bernoulli. I just want to know what my parameter is. And that's sort of the claim I made back here, right? Was that
Could have made it geometric and done the same thing.
yeah, so geometric is a little bit odd here because there's never anything but 0 or 1, so it's probably going to be Bernoulli is pretty good for this one. But yeah, if you have, say, a distribution over the continuous, or sort of over positive integers or even non-negative integers, you could choose between geometric or Poisson, right? That would actually be minus the fact that one has a 0, one doesn't have a 0. But if you have, the right, if you subtract the thing properly to make them all, say, between 0 and an infinite, you can choose, is it a geometric distribution or is it a Poisson distribution? I'm not talking about that here. This is actually a very hard thing because once you have sort of, say even integer value data, there's a huge number of distributions you could actually pick from, right? And you can't directly compare. There's actually a lot of reasons why, just like with overfitting, you can't directly compare different distributions by their likelihood. That will sometimes lead, more complex distributions will always have higher likelihood of the data. Up to the point where the most likely distribution for any set of data is just the empirical distribution that just only thinks those points are the only ones that will ever happen, which is not what you actually want here. So what you're really doing here is we're talking about, given a fixed family of distributions, how do I find the parameters that maximize the probability of that observed data? You're on your own for picking the distribution so far. There we go. Okay, and by the way, this same principle holds virtually for any distribution. So I'm not going to go through this one here, but just, you can look through it, and I'll even try it if you feel like it, or if this seems completely opaque, I actually encourage you to derive these things. If you look at a Gaussian, for example, the Gaussian distribution, write the log likelihood of some amount of data. So here xi's are going to be real valued numbers that describe data. And if you do the same thing, so write the log likelihood, take the derivatives with respect to the parameters of the distribution. In that case, this is going to be the mean and the variance. Set those equal to 0. What you'll find is that the estimate for the mean you get is just going to be the empirical mean of the samples. It's 1 over m times the sum of them. Similarly, the variance you get is just going to be the empirical variance. So it's 1 minus the 1 over m times the sum of xi minus mu squared. So if you do the same exact procedure for a Gaussian, you get the fact that the parameters the Gaussian should have are in fact the just these terms here, the empirical mean, what's called the empirical mean because it's just the sort of the mean of the values there, and what's called the empirical variance here. Now I should say that this is not the only way to estimate these things. In fact, if you use a different estimator, one that is not the maximum likelihood estimator, you actually get a different denominator here. You get m-1 there, which is this actually very odd thing saying that if I'm estimating both my terms, I should actually inflate my variance a little bit to account for the fact that I'm not sure of my sample. That comes from something called an unbiased estimator, but we're actually going to ignore that. We're just going to talk about maximum likelihood estimation, and in that case, you actually have just the 1 over m term. If that wasn't familiar to anyone, don't worry about it, but just if you've seen that m-1 before ever, that's why. That's where it comes from. Okay, so lastly, we have 15 minutes now, and I probably will not take questions just because I want to get through this, because on the homework, we'll talk about naive Bayes. Okay, so naive Bayes is a machine learning algorithm, really one based upon Bayes' rule. And the reason why I'm talking about it, actually, is that as far as algorithms go, it's kind of lost a little bit of favor recently. It isn't that common to apply because other techniques typically work a little bit better, in most cases at least. But it's a very nice combination of machine learning and probability, sort of that both this lecture and the next one, the little bit in the next one actually, I'll sort of emphasize the common theme to all these things. But it's a very sort of nice way of seeing how you can use probability to essentially make predictions like you do in machine learning. So the idea here is that we have a random variable x. So, okay, switching gears now. Have a random variable x. And this variable actually has many variables within it. x1, x2. So this is actually a multidimensional random variable. And actually, these can be anything. These can be Bernoulli. They could be categorical. They could be Gaussian. Could be Poisson, too, if you want them to be. But they can be any distribution. Then we also have y. And y is actually just going to be either categorical or Bernoulli. We'll always assume it's either. And in fact, I think for this lecture, I assume it's always Bernoulli, even. Though the extension to a categorical variable is pretty straightforward. And our goal of this is that we want to find p of y given x. So now let's go back to our sort of machine learning setting, right? Our machine learning setting was we have some inputs that describe kind of our data, right? Our data is described by this. We have some outputs. This is things, for example, like on your homework, is the digit that you're observing here a 0 through a 9? Is this email spam or not? We are talking about classification here, so we're going to be talking about the discrete case of y, not the continuous case. So yeah, is the tumor malignant or benign? And x are the features, right? X are the inputs that we want to use to tell us that. Now, in our previous approaches, we didn't actually build a probability model over the inputs themselves. And what we're going to do in naive Bayes is actually model the distribution of each of these inputs. And we're going to do that using Bayes' rule in the following way. So Bayes' rule says that the probability, if we want to compute this probability, right, we take the probability of x given y times the probability of x, probability of y, sorry, divided by the probability of x. And this, don't worry about the denominator here. The denominator you can get by just summing over all values in the numerator, so we're going to ignore it. For the most part, we're going to focus on this numerator term here. So if y is either categorical or Bernoulli, we kind of know how to model p of y, right? P of y is just going to be a Bernoulli random variable, say. It's going to be estimated by essentially counting how many times you see the different values of y. The term p of x given y, though, this term is trickier because this is a big random variable, right? This is sort of a nasty random variable that has lots of different elements of it. And remember, in our thinking, this expression here should say, you know, for any possible assignment of any of these variables, I have to know what my probability is here. Or if it's a continuous variable, it's what my probability density is. But if I have, you know, 10 categorical variables here, I therefore need to describe the entire joint distribution of p of x for all possible values of y, right? That's going to blow up very quickly. We're very fast going to have too many distributions, or too high-dimensional distributions to actually capture this term here. So what naive Bayes does is it makes what's called the naive Bayes assumption. And the assumption we're going to make is that the features are going to be conditionally independent given the output y. So our naive Bayes assumption this is not true in general. This is not true of general probabilistic models, but this is what we're assuming, is that the probability of x given y is equal to the product from I equals 1 to n of individual distributions, xi given yi. And now, importantly, these things are not that hard to model, right? If these are discrete, say the x's are discrete, it's not that bad to model a distribution of, you know, all possible settings of what xi is and all possible settings of y. What is that probability going to be? But just to emphasize too, we actually, and I'll mention this only at the very end, and you actually are doing it for your homework. You can also use other distributions too. So the xi's could be, say, real valued, and you use a Gaussian distribution. You just one Gaussian for xi being, for y being equal to 0, one for it being equal to 1. Okay? And you specify this distribution, this whole conditional distribution here with just multiple, you know, continuous value distributions, one for each value of y. This is actually why we don't bother here with multiple possible values of, or continuous values of y, because if y is continuous valued, these actually do become hard to define then, what this even really means. So we're going to worry about discrete, finite values of y here. Okay, so let's say now that everything's Bernoulli, just keep things a little simple. What we would do essentially here is model for each xi, we model xi given yi, and I'll write this as, you know, given yi equals little y, because what we're actually going to do is we're going to specify a separate distribution for each value of y here. This is going to be described by a Bernoulli distribution with the parameter that I will call, what do I call it again? I call it phi I superscript y. But really what I mean by that, and again, I'm being a little bit pedantic here because I want to emphasize that this is not just restricted to counting. You can use any distribution here. But what I mean by this is I'm going to specify this distribution by this Bernoulli distribution, which is specified by this parameter phi, which is, in other words, is equal to the probability that this thing equals 1, given that y has a certain value. Okay. And now, of course, if we want to actually compute the estimates for these parameters, well, we just use maximum likelihood estimation, just as we did before. And using the exact same logic as before, what we'll get out is we'll get out, and you can do this, by the way. If you really want to, you can actually write the likelihood down, take the logs of it, take derivatives with the parameter, and you will get these things. But what you get in the end is kind of exactly what you would expect to get. The estimate for phi 0, and phi 0 is just a Bernoulli over y here. It's just essentially the number of times y is equal to 1 divided by the total number of samples. That's just normal. That's just how we estimate this thing, kind of as we expected. And then the next one is going to be phi y subscript I is going to be the sum of the number of times we see xi here. So this means the xi is positive, xi is equal to 1, times whether or not y, in this example, yj is equal to y. So again, this y here varies over 0 and 1. And so we do this once for looking at all the times where y is equal to 0, and once for all the times where y equals to 1. and we just compute the probabilities there. I have an example in a second that we'll go through, which will hopefully make this a little more clear. But that's the way you estimate these parameters. And these things here just fall out of maximum likelihood the same way our Bernoulli example worked before. OK, so which slide am I on? OK, so the last thing I'll say now is that once I have all these parameters that describe my distribution, and you get them essentially just by counting, right? I mean, it really is maximum likelihood estimation. But really, for the case of everything being Bernoulli, it's just kind of counting. The way you get a prediction now is that if I am given some x, that means that I'm given values for all x1, x2 to xn. I just plug in these values into my distributions that I've computed for all possible values of y. So to compute the probability that y equals 0, I would compute the probability that y equals 0 times the sum of the probabilities of xi that I observe given that y equals 0. And I would do the same thing for y equals 1. And the expression you get is just this expression here. Those are all terms that you've estimated from your distributions, but really they're actually even easier than that, because in the case of Bernoulli, this is almost just, this is again using my kind of fancy way of writing these things. You just basically plug in the data you see, compute the probability of that for each variable, and then when you want to actually have a probability, you just normalize by making sure all these probabilities sum to 1. So let's actually do this though, because this is getting a little bit abstract. It's actually really straightforward. So here's an example, which actually did not compute yet. Hopefully the numbers are not silly, but I have two input features here, and the output, all of them are binary valued, right? So what is my probability that y equals 1? That's described by a Bernoulli variable, which is going to be phi 0. What is phi 0 here? So I have 7 examples, and 4 of them are 1s, so phi 0 is 4 over 7. What's the next one? What's the probability x equals 1 given y equals 0? What is it? 1/3. So I have 3 times y is equal to 0, and one of them x equal to 1. So phi 1 of 0 equals 1/3. Or my other ones, what's this? Phi 1, 1. What's the probability that x equals 1 given y equals 1? I have 4 times, and it's 3/4, right? My next two. What's probably x2 equals 1 given y equals 0? A third also, right? 1/3? Yell them out. I haven't done this before, so I'm just looking over there as well. Phi 2, 0 equals 1/3. And then what's the probability of that x2 equals 1 given y equals 0? One-third. No, something fourth. There's 4 times y is equal to 1. 1. Sorry, what were people saying? Yeah, it should be y equal to 1. Sorry. That's just 1/2. Is it 1/2? Y equals to 1. Yeah, 1/2. Okay. So now, if I want to compute my final probability, say I have some new column I've never seen before. Does everyone understand how I did that? You just basically filter on the times where y is equal to 0 or 1, and just compute the probabilities, which what we're really doing is we're doing maximum likelihood estimation, but you don't have to call it that. And now if I want to know what the probability that y equals 1 given x1 equals 1 and x2 equals 0, say, well, I just plug it into my rule up there. So that will be equal to, it will be actually proportional to the probability that y equals 1, which is just going to be phi 0. Phi 0 times the probability that x1 times this guy, given this times phi 1, 1 times phi, or sorry, 1 minus phi 2, 1. 2, 1, yep. And then I divide this by the same thing, phi 0, phi 1, 1, 1 minus phi 1, 2, times the probability that y being equal to 0, which is 1 minus phi 0. And this one would be phi 1, 0, and 1 minus phi 2, 0. I might have made a mistake there, but that's, I don't know what that number is. You can just compute it if you want to. But that's how I do these things. That's how I compute the probability of y being both 0 and 1, because obviously the probability is equal to 0 is just the 1 minus that thing, and go from there. 2 issues I'm going to take 2 more minutes to describe because it's going to happen on your homework. So 2 issues. First one, if you compute this product out numerically, you will run into numerical issues. You will get it to be equal to 0 because your numbers will overflow in floating point. To avoid that, use logs instead. So instead of computing the product of these things, compute the log of these things. The log of the product, which nicely separates this out. Oh, okay. Problem number 2. If you're in a case where you have some, maybe I have a lot of different classes, a lot of different y's, and I encounter a case where I've only seen one value of an xi for that yi, I will get potentially a 0 or a 1 probability. And a 0 probability in this whole thing will be really bad, because if you take the probability of everything, then goes to 0. So it's common to use what's called Laplace smoothing. That involves just adding 1 or however many 1 to the numerator, and then however many outputs there are to the denominator. And finally, the last thing is that naive Bayes is often presented like this, where it's just about counting and making counts, right? But the nicer thing about our sort of notation, of our notion about what we're really doing here is we're using maximum likelihood estimation to estimate the distribution of xi given y for all values of y, is that you can just as easily plug in any distribution you want for xi. So I could, for instance, just plug in a Gaussian if xi is real valued, right? I have a separate Gaussian now describing xi for each possible value of y. Sorry, not yi. Right? And you actually estimate them. And if you plug in the whole thing, maximum likelihood estimation, you get something very similar, which is exactly what you think. You get something like the mean, only counting those examples where y is equal to the actual y term, and then the variance. Oh, that should be squared there. Should be squared. Oh, it's auto recovery is saving the file before I can add this to square it. Oh. And of course, it doesn't actually work when I do it in real time, so this should be squared here. That should be a squared term. I'll fix it in the notes. But the basic point being that you can actually use any distribution you want for these xi's. They are not limited to being Bernoulli or even categorical and just being about counting. This actually can be a very general algorithm where you try to actually model each of the distributions of the yi's given that discrete value, that particular value of y. And doing that, you can come up with all sorts of situations where we can say, do the same thing we did for the cancer data set, where we have continuous valued inputs and only discrete binary outcomes. We can still model those same kind of problems with naive Bayes. OK. Thank you for getting through that. I'll see everyone on Monday.